Hi everybody, this is my project 3 and I'm looking at linear equations in GPS. So I'm Abby and I'm studying ecological engineering, and GPS is used often in my field of study through surveying. So this summer I had an internship where I went out in the field and used surveying equipment on property. And so here's an example of an RTK right here, which is something I used. And surveying is used often in my field of study because we may want to understand a watershed more accurately, re-engage a floodplain, and we need to know what that floodplain looks like, or propose a site plan. So this means that we need to gain models of Earth's surface. So with an RTK, it's connected to the satellites and it's geographically located that way. So we can go around property and basically take pictures of different points on the property with different elevations, and then use a thumb drive to put that data right into the computer and put it into software such as AutoCAD, Civil 3D, and create a model from it. And it's much simpler than other older fashions of surveying where you have to shoot a laser beam and get it reflected off of something, because you have to geographically locate that later on the computer, whereas this is using satellites, so it is already geographically located once you put it into the computer. So what is GPS? It is Global Positioning System, and linear equations are used to determine geographical locations through dimensional triangulation. So that's basically where you would find a point on a surface of the Earth and determine its distance to 3 other points to figure out where it is. In real life, it's much more complicated than what I'm going to show. You have to take into account travel time for radio signals, general relativity since satellites are very far away and fast moving, inaccuracies in the time between the GPS unit and the satellite, and the way radio signals pass through the Earth's atmosphere. But in this example, we are assuming exact geometric knowledge, and we're only looking at 4 satellites, whereas in real life there may be many more satellites than that. So here's our coordinate system. It's basically a 3-dimensional coordinate system where the Earth is at the origin, and we are using units of the radius of the Earth for simplification. So here's a 2D example that I think is much easier to think about. Imagine your GPS system says you're 39 kilometers away from point A, 50 kilometers away from point B, and 29 kilometers away from point C. And that might not seem very helpful, but your GPS is only able to locate places that it knows where they are, right? So there might be a satellite tower in each of these places. And you can figure out where you are by looking at the intersection of all 3 of these points. So the circles. So you're right here at this point, and you could use a matrix to solve this also. And in the case we're looking at, we're going to have spheres instead of circles. So I'm looking at an example from Dan Kalman, and if you want to go more in depth on how it all works, you can go more slowly through my presentation. But basically, this is the data that we're looking at a ship somewhere on the Earth, and this is the data the satellites return. We're looking at 4 satellites. So using the speed of light, we create these equations here, and the equations are not linear, which is why we have to do more algebra, which is shown all this how to do here, and this is how you get these 3 linear equations with the 4 unknowns here. So what we're going to do is put this into an augmented matrix, which I've shown here, and then row reduced echelon form right here. And this gives you, these are the answers for our variables where t for time is free. So this means that we can basically substitute back into the original equation to get a quadratic form here. And using the quadratic formula, we get 2 solutions, right, where t could equal this or that. And so I plug them back into the original equation, and I see, oh, one of these gives back a distance with that is 2 Earth radius away, and one that is about 1 Earth radius away from the center. So we know it has to be a time of 50, since the ship is on Earth's surface. It's not about 4,000 miles above the Earth's surface. So when we plug time equals 50 back into our equation from earlier, this is the point we get. So we were able to solve this using augmented matrices and putting it into row reduced echelon form, which you can easily do with Octave on the computer and just program that in for you. So we found our ship's location, and this would probably be more useful in real life if it were in longitude and latitude, but that is a whole nother problem for a different day. So the big concept here is that we are able to use matrices to easily solve linear equations with many variables, much easier than before. So in the past, we would have had to use elimination, substitution, or graphing, which could get very messy with all of these different equations and variables at the same time. But here, we are able to do it very swiftly with just a matrix. So thanks. Let me know if you have any questions. And here are my credits if you want to go take a look at the longer version of Dan Kalman's example. Thank you.